Magic can be used for good or bad, and today we'll be talking about both kinds of magic. But there will be no foolish wand waving or silly incantations in this talk, because I'm not actually a wizard. I bought this wand at a toy store. My name is Joe Kutner. I work at Heroku. Heroku is a platform as a service. We host more than 10 million applications and handle about 23 billion requests per day. My job there is the Java language owner, so I'm responsible for curating the Java experience on the platform, making sure our Java customers can deploy and have a good time doing that. One of the tools I have for doing that work is called Buildpacks, and that's something I'll talk about later on. Before we dig in, I want to make one thing very clear. When I say Docker and I say Dockerfile, I'm not talking about the same thing. Docker is an ecosystem of many different technologies, servers, APIs, specifications. Dockerfile is one of those tools in that ecosystem. A Dockerfile is a mechanism for describing how a source code repository becomes a Docker image. And it's just one of the tools we have to do that. So I will say some bad things about Dockerfile today, but just know that when I say them, I don't necessarily mean that about Docker. So to understand why there are problems with Dockerfile, we first need to practice the Docker arts to protect ourselves from them. So we're going to walk through how you create a Dockerfile for a very simple Java application. And this isn't a contrived example. I'm actually going to walk through the steps that are described in a blog post on docker.com for how to create a Dockerfile for a Java application. In this post, they talk about making sure that you are copying files into the image in the correct order. So if you were to copy your application source code in before you install the JDK, every change to your Java files would invalidate the cache layer for the JDK, and you'd have to reinstall it every time you built, which would be very inefficient. Similarly, we want to only copy into the image what we need. So we don't want to copy extra files that might bust our cache unnecessarily. It's also just good to avoid wildcards so that you're not copying secrets into the image and things like that. Another way that we want to optimize our layer caching is by putting line buddies together. So if we're installing the JDK and also updating the package indices for apt, we want to do that on the same run directive so that they become invalidated together. And ultimately so that they only create a single layer. And that layer, because of the way apt works, is going to have some cruft in it. So we also want to add to that RMRF these extra files that we don't need at production. They're only there to install the JDK. So this is a pretty tame example of having a single run directive doing multiple things, but it can really get out of hand. If we look at the Dockerfile for the official Python image on Docker Hub, it has a 112-line run command, which I actually couldn't even fit on this giant screen. But if you look closely, it's a whole bunch of bash commands ampersanded together so that the Python runtime gets installed on a single layer without any cruft left behind. This is what I like to call Dockerfile gymnastics. You do these kind of weird contortions to get Dockerfile to bend to your will. Fortunately, a lot of these steps can be encapsulated into a base image. So what I've just described is exactly what happens in the official OpenJDK image, which is on Docker Hub. But you shouldn't use that image because it can't be trusted. There's been a couple incidents where this official OpenJDK image actually contained an incorrect JDK. And that's because the apt package it installs was built from an incorrect tag. So it would advertise itself as 8 update 202, but it was not actually 8 update 202. This is not a problem that's unique to Java. The folks at SNCC took a look at the most popular Docker images on Docker Hub, and they found that each of the top 10 contained at least 30 vulnerabilities, each. So it's sort of like CV as a service. If you're using these images in production, your trust might be misguided. And this is why a lot of organizations aren't using Docker Hub, but instead they're building their own images, their own base images from scratch. But whether you're using an image from Docker Hub or using your own, you want to make sure that you're using the correct tag. If you're using OpenJDK latest, for example, you probably don't want JDK 14 early access in production. You want to be specific about what you're using. But because of the way Dockerfile works, our tags get fairly verbose because they have to refer to everything that's in the image. So we end up with this kind of combinatorics problem where every time you add a new dependency to the image, you have to refer to that into the tag. There's no way to like merge two images together. So for Java, at a minimum, we need the major version, JRE versus JDK, the operating system flavor. As a result, just from those few things, there's more than 2,500 tags, or almost 2,500 tags on the OpenJDK repo on Docker Hub. So make sure you choose wisely because the image does not choose you. You choose the image. We also probably want to run our Maven build in a container, so let's throw Maven into that combinatorics problem. So we can modify our Dockerfile so that it's using a Maven base image, Maven 3.6, JDK, 8, Alpine. But when we start to build our application in a container, we have to do more Dockerfile gymnastics. So if we just copied all of our source code in at once and then built it, we'd never be able to take advantage of that Maven dependency cache. So it's pretty common to copy your POM XML into the image first, then run Maven dependency resolve, then copy your source code in, then run Maven package. And so in this way, changes to your .java files will not invalidate your Maven dependency cache. However, changes to the authors in your POM XML will still invalidate your Maven cache for no reason. If you have a multi-module Maven project, you have to copy all of those POM files and keep it in sync with your repository. So it can get kind of messy. We don't want to run Maven in production, so we're going to have use multi-stage builds to copy the jar file out of that Maven container and into a new image. This works pretty well for a single jar file, but you can't use this mechanism to, for example, copy a Node.js runtime into your image. Multi-stage builds won't follow symlinks, they won't copy environment variables. That's not really what they're meant for. But in any case, this is what the folks at Docker recommend for a very basic Docker file for a very simple Java application. What you should take away from this is not what this Docker file looks like. It's look at all the things we had to know to create the simplest possible Docker file. We had to basically speak parcel tongue, right? At the end of the day, Dockerfile is a leaky abstraction. It exposes to the author of the Docker file all these mechanisms that make it work, how the layer caching system works, how the OCI image format is structured. You have to understand these things in order to use Dockerfile effectively. What's worse is that we have to repeat this process every time we have a new Java application. We have to create a new Dockerfile for that app. In the best case scenario, we're going to copy and paste our Dockerfile into the repository, which is, of course, a code smell. But in the worst case scenario, each project is a little bit different, has different Maven modules, has a little bit different structure, different external dependencies, and we're going to copy and paste bits and pieces of our Dockerfile into a new Dockerfile. Some people use templates to make this easier, but in any case, you are propagating your configuration throughout the many repositories that you have, and you end up with these snowflake applications that increase your operational burden. Now, everything I've just described is the problems on day one, right? Just creating a Dockerfile. But the real problems with Dockerfile start on day two, when you need to make changes to that image, when you need to update your dependencies. So to illustrate this, let's take an example, Heartbleed. This was a very bad bug that affected OpenSSL, or was a vulnerability in OpenSSL. So it didn't affect Java directly, but it affected any image that had OpenSSL in it. So it was a very, very broad impact, which is why I've selected it. So if we look at the typical Java application image, it has at least 3 sets of layers. You have your application layer or layers, you have a layer for the JDK, and then below that you have your operating system layers, which will be Ubuntu and your system packages and whatever else it is. Because of the nature of this vulnerability, it required a patch at those operating system layer level. And because of the way Dockerfile works, any change to those layers will invalidate the layers above it and force you to re-download and install the JDK, re-download the internet for your Maven dependencies, recompile your source code, all unnecessarily. None of that has to happen because the external interface of the operating system stayed the same. So this is a process that can take hours in the worst cases, and that's just for a single application. I think most of us have many apps, and because of the breadth of this, the broad impact of this vulnerability, every one of those images would have to be rebuilt. So now we're talking about reinstalling the JDK on every image, re-downloading our Maven dependencies for every image, recompiling our code. In the worst cases, if we have those Snowflake Docker files, we've got different operating system flavors, different JDK versions, and so we have to go through each repository and sort of customly update them. This can extend the time it takes to mitigate something like Heartbleed to months, and it gets really bad when everybody has that app that's been running in production for years. Nothing's wrong with it, so you didn't change it. And now to update OpenSSL, you have to recompile it, and for whatever reason, it doesn't build, right? So now you have to spend development cycles to get that thing working. Maybe the source code is gone. Good luck, have fun. That can really extend the ETA to mitigation out to years in the worst cases. Spoiler alert, though, on Heroku, our users did not have to do anything to be protected against Heartbleed. Their apps were updated overnight. And I'll explain how later on. So again, just a reminder, when I say Dockerfile and these things I'm sort of criticizing it for, I do not mean Docker. They are two different things, and Dockerfile is just one mechanism that we have to turn our source code into a Docker image. So in the next part of this talk, which I call advanced image making, we're going to talk about some of those alternatives. Advanced is kind of the wrong word because some of these alternatives are actually less advanced than Dockerfile, which, as we've seen, can be kind of complicated. But the first example is very advanced. It's called BuildKit. This is the library that powers Dockerfile, actually. So it comes from the folks at Docker. They extracted it from their sort of core code base so that it could be reused. The idea being that you could put other front ends on top of it, other interfaces on top of it, like Dockerfile, to build your own image building tooling or mechanisms. So at a very high level, it works by taking your application source code as input. It runs some kind of front end against that, which could be Dockerfile or something custom that you wrote. It generates an intermediate format called LLB, or low-level build format. And then BuildKit, the engine, uses that LLB to generate a Docker image. So the library is written in Go, as much of the Docker ecosystem is. So you have to use Go in order to use BuildKit. But if we look at the API for it, you'll see that it kind of maps fairly closely to the Dockerfile directives. We can run commands, we can add environment variables. But because we're working in a higher level language, we have a little bit more power to do some more advanced operations. But at the end of the day, BuildKit is not a tool for application developers, it's a tool for tool developers. So maybe you have some custom processes, build processes in your organization that you want to make your own tool for. As long as you're comfortable writing Go code, this might be the tool for you. It allows other front ends that other people have built, including Dockerfile, and works with Dockerfile. But it does support features that are not supported in Dockerfile, like direct data mounting and an exportable cache. So, for example, you could write a tool that took your your Docker cache and then shared it amongst developers in your org or something like that. The downside is that it's written in Go, so unless you're comfortable writing Golang code, there might be a learning curve. And again, it's not for application developers. This is not for the Spring Boot developer who just wants to add features to their application. A better tool for that person is Jib. This is a Java library from the folks at Google, created to build Docker images without a Docker file and without Docker itself even. It is, as I said, a Java library, but it integrates with our build tools, including Maven and Gradle. And at a very high level, it takes your application source code as input. You run a Maven command against it. And because Jib is built into a Maven plugin, it knows about that Maven environment, uses the artifacts that are generated from the Maven build to create a Docker image. So we use the Maven plugin just like any other Maven plugin. I think the only configuration that's required is the name of the image you want to produce. There's some other configuration options, but for the most part, it's really simple. It's what an application developer who works with Maven and Spring or whatever it may be is familiar with. Once we have the plugin, we just run Maven commands like we'd run any other Maven command. We can run Maven Jib build to create an image directly on a remote repository, which is essentially a JSON file written out to a remote repository plus some tarballs. But that doesn't require a local Docker daemon. So you can actually run Maven Jib build without installing Docker on your local machine. If you do want to use that local Docker image, maybe to validate it or test it or just go through some kind of dev cycle, you can run maven gib docker build, and it'll write that image to your local registry. So here's what it looks like. I'm running maven clean compile on a just simple Spring Boot application. You can see it goes through the normal build process, and then at the very end, it exports that Docker image. Just like any other Docker image, I can run it with Docker run. I can Docker push it. There are some configuration options within the plugin for what base image you're using. You can add environment variables, change some directories. Some very basic things, but it's not a super powerful configuration mechanism. So the pros of Gib are that it's developer-oriented. This is a tool meant for people who want to write Java code and don't want to care about the infrastructure that goes with Docker. It's daemonless. It doesn't even require Docker to be installed. And it's Java native. So it understands our Java ecosystem. We don't have to tell it where Gradle put our build artifacts. It knows where our build artifacts are. The downside is that it is Java only. I've heard that the folks at Google are working on Gib for other languages, but even if those do successfully ship, you're talking about discrete libraries for different languages, which makes it difficult or maybe impossible to have a unified build system. That is a build system where people in your organization can audit it in a consistent way and understand what is going into your images to perform security review or whatever it may be. It's also less portable because it's running as part of Maven. So Gib doesn't do anything to control the Maven execution itself. So if you want to run Maven in a container, you may have to back out to Dockerfile to do that. It also doesn't help us with keeping our Maven cache around so that we can optimize our builds. And it's also not very extensible. It has some configuration options, as we saw, but it doesn't have a mechanism for combining images, bringing in external dependencies like a Node.js runtime or something like that. Now, if we want a tool that is great for application developers but has all the power of something like BuildKit, that's where buildpacks.io comes in, or Cloud Native Buildpacks. Cloud Native Buildpacks is a sandbox project in the Cloud Native Computing Foundation, which is the home to Kubernetes and all of those cloud native technologies. Full disclosure, I'm a founding member of this project, so I am very biased, but hear me out. The Buildpacks were based on, buildpacks.io was based on a technology that was created by Heroku, and it's what Heroku uses to build and prepare your application for production, for runtime. So if you've ever used Heroku and run git push Heroku master, or if you use Cloud Foundry and run cf push, in either case, you've used a Buildpack. The Buildpack detects what kind of application you have, it installs the necessary dependencies, it runs Maven, and does whatever it needs to do based on the language. Buildpacks were created about 8 years ago. They were actually created as a mechanism for Heroku to grow from what was at the time just a Ruby on Rails platform to a polyglot platform where we supported Java and Node.js and many other languages. So we used Buildpacks to modularize this support, but we also used it as an extension point for our customers. So our customers could bring their own Buildpacks to add support for Rust and R and C and Minecraft. You can do anything with a Buildpack that you can do on Linux. So buildpacks.io was an effort to take those ideas from Buildpacks that we've been using in production for a very long time and marry them with the Docker ecosystem. So instead of producing a proprietary image format that we use on Heroku, we would produce standard Docker images. So at a very high level, Cloud Native Buildpacks take your source code as input. They detect what kind of application you have by looking at the files and other information about the app. And as output, they produce a Docker image with layers that map logically to your application, as opposed to layers that are arbitrarily derived from directives in a Dockerfile. So the Buildpacks themselves are just one part of the broader Buildpack ecosystem. There's also the parts of buildpacks.io that run Buildpacks. So we have the platforms, and there's a specification for what a platform is, the thing that knows how to run Buildpacks. There's the implementation, which we call the lifecycle. This is actually the code that runs the Buildpack itself, and then a whole bunch of specifications around these things. So to visualize this, at the very top we have the Buildpack implementations. These are what run against your code. Below that, the engine that runs it. And then at the bottom, a platform which supports the whole stack. Between each of these layers is a well-defined API, which allows us to swap in and out different implementations of each of these components. So for example, you can have a Heroku Java Buildpack or a Cloud Foundry Java Buildpack or a Node.js Buildpack, or you can write your own. At the bottom, we have different kinds of platforms. Pack is one that we're going to talk about today. There's also Kpack from Pivotal, Tekton, which was originally Knative Build. It can be used as a Buildpack platform, and of course, products like Heroku. So Pack is a platform, but it's a platform that's meant for local development. It is a CLI that you can use to run Buildpacks locally or in any other environment. If you're on a Mac, you can install it with Brew. We also have installers for Windows and Linux if you go to buildpacks.io. But in any case, once you've installed it, the first command you'll probably run is pack build, and then the name of the image you want to run. And this will execute against your current working directory. We're going to pass the Heroku Buildpacks builder image, so we're telling Pack to use specifically the Heroku Buildpacks when it runs against our application code. So this is what it looks like. I'm going to run this against that same Spring Boot application. The first thing it'll do is detect that it is a Java app. I've already run this once before, so it's going to restore some cache things. It installs Maven, runs Maven using that Maven dependency cache, detects what Java command should be used to run this application, exports an image, and then you can see with Docker run, just like any other Docker image, it starts up my Spring Boot app. So the main thing to take away here is, look at all the things I didn't have to do. I didn't have to do anything. I just ran pack build against a Spring Boot app. I didn't have to modify the POM XML. I didn't have to add any external or any other configuration. Buildpacks sit outside of my application so that I don't have to worry about those infrastructure concerns. But at the end of the day, I still get an OCI image, and I get an OCI image that's structured in a way that makes sense for my application rather than arbitrarily derived from commands in my Dockerfile. This structure of the OCI image allows us to do things with Buildpacks that you can't do with other tools. Because we have structured layers that map directly to the different components like the JDK and the application, we also have a configuration layer that contains metadata that tells us what version of the JDK is in this layer. So there's some very powerful things that we can do. For example, we can inspect the image by running pack inspect image, which will give us a bill of materials for that image. It'll tell us what Buildpack ran against this app to create the image, what version of the JDK is in there, and then depending on the Buildpack and whether it's a Node or Python or Java Buildpack, it will tell you other information. So Buildpacks have some characteristics that make them a better tool than something like Dockerfile. To begin with, they're reusable. So you use the same Buildpack many times as opposed to creating a new Dockerfile for every repository. And those Buildpacks are well tested. The Heroku Ruby Buildpack has been running in production for 8 years. It's very powerful, it has many bug fixes, and it's something you can depend on to build your apps. But in any case, whether you're using an off-the-shelf Buildpack from Heroku or Cloud Foundry or writing your own, you do that once and you can reuse it. Buildpacks are fast. They only rebuild and upload layers when it's absolutely necessary. If you're upgrading your JDK version, it will install the JDK. But if you're not, and you're updating your operating system, it'll keep the same JDK. It's intelligent. It's app aware, so it knows what it needs to do, when it needs to bust your Maven cache, and when it does not. Buildpacks are modular, so you can combine them together to create composite images. So a great example of this is like your typical JHipster application where you have like an Angular.js front end and a Spring Boot back end, and you need a Node.js runtime and a Java runtime to build it and prepare it for production. With Dockerfile, this is requires some custom work, but with Buildpacks, you just combine the JavaScript Buildpack with the Java Buildpack, and they'll run against your app. Buildpacks are also safe. They allow you to meet security requirements without developer intervention. So in order to update SSL, we do not need to make any modifications to our code. They separate the application developer from those infrastructure concerns. So as I said, you will probably, if you use Buildpacks, you'll probably use an off-the-shelf Buildpack, but I think it's worth talking about how Buildpacks work, what the Buildpack API is, so you can understand some of their capabilities and some of their value. So the Buildpack API, at the end of the day, has two entry points, detect and build. There's also two internal phases that authors don't have to implement, but run as part of the execution. The detect phase is where a Buildpack determines whether it should or should not run against a particular application. Sometimes this is very simple. Most Java Buildpacks look for a POM.xml, and if they see that file, they know it's a Maven application or a build Gradle. Other Buildpacks have more complicated strategies. They'll check to see if, like, an APM is provisioned and attached to this application, if it should install some agent or something like that. But sometimes it's very simple. The next phase is analysis. This is where the execution environment looks at the metadata from the detect phase to determine if it can reuse some of the cache. If it has access to a previous build, it'll reuse layers from that image. The next phase is build. This is where the sort of heavy lifting happens. This is where we install the JDK. This is where we run Maven, and all that's implemented as part of each unique build pack. The last phase is export. It's where we take the artifacts derived from the build and produce a Docker image, and then also a cache image, or if you're using something like Tecton, it might be just written to disk on a volume. But at the end of the day, you're exporting two artifacts. So if we walk through this process on that example JHipster application, we're going to have a POM.xml, or a source code repository with a POM.xml and a package JSON. When we run like a command like pack build, the first thing that'll happen is the Java Buildpack detect phase will run. It'll pass because it sees that POM.xml. And it's going to output what we call a build plan. This is how we create the bill of materials. It'll emit what version of the JDK needs to be installed, and then any other metadata. Then the Node.js Buildpack will run, and its detection will pass because it sees that package JSON file, and it's going to add to that build plan. It's going to write into it what version of Node it's going to install and any other information it needs to emit, maybe whether it's using NPM or Yarn, that kind of thing. Then the Java Buildpack's build phase will run, and as input to that build process, it's going to get that build plan, so it will know what JDK version to install, and it'll produce a JDK layer. And then potentially a jar layer for your dependencies, maybe other layers for your application itself. Then the Node.js Buildpack will run. It'll take that same build plan, and it'll produce the Node.js layer. So if we were to look at this with regard to those phases, we'd see that the first phase is detect. We have both Java and Node Buildpacks passing because they were detected successfully. The analysis phase will do nothing because this is our first build. There's no cache, there's no previous image. The build phase will do all the heavy lifting, install the JDK, run our build tools, and download dependencies. And then that last phase will export all of the work done by that build phase into our OCI image. The second time we run a build, let's say we've changed our dependencies. We've changed our Node modules or our Maven dependencies in the POM.xml. We'll still pass detection because we still have those files around. This time our analysis phase is going to use the configuration layer that was written to the OCI image to determine from that metadata what can be reused, what layers can be reused, and what parts of our cache can. So now during the build phase, it'll read metadata from disk to recognize that we don't have to reinstall the JDK because the version is not changed. We do need to run Maven so we can get our new dependencies, but it will have that Maven cache, so it's not going to have to download the internet. So it'll update the jar files that go into our app. It'll update our Node modules. And then during the export phase, it'll update just the layers that changed. So the Node.js layer will stay the same, the JDK or JRE layer will stay the same, and we'll just get those layers that either represent our app or our dependencies. Okay, so now that we know how Buildpacks work, let's return to that Heartbleed example. With Dockerfile, as you recall, we had our image structure, 3 different sort of sets of layers, and we have to patch those operating system layers in order to remediate Heartbleed. But with Buildpacks, those upper layers were produced from a Buildpack, and we have that configuration, so we know what's contained in those images. And our operating system, what we refer to as our stack, has something called ABI compatibility. This is a guarantee provided to us by certain operating system vendors, such as Canonical for Ubuntu, where they guarantee a degree of compatibility when patching system packages. So when Heartbleed came out, there was an updated version of OpenSSL, but they guaranteed that the external interface of that package did not change. What that means is that we don't need to change our app, right? So if we have our old image sitting atop the vulnerable operating system and a new image comes out, as long as we have that ABI compatibility, we can do this sort of lift and shift, where we just take those layers and move them onto the new image to create or we move them onto the new stack to create a new image without actually running any of our build processes. This can reduce the ETA to mitigation from potentially years to maybe just hours. So there's a process we call rebasing in Buildpacks, and this is what it looks like when you use the pack CLI. We're running pack rebase on an image I've already created, and within a few seconds, it's given me a new image built upon that updated stack. I think the slowest part about this is actually writing to the console. It's literally just modifying a JSON file and sending it up to our Docker registry. So this is powerful stuff. This is what I call magic. We've talked about a whole bunch of options here, but which one is right for you? I think it's worth looking at what kind of work you do and which tool solves the problems that you have. So first there's Dockerfile. I've disparaged it a bit, but it's still a useful tool. In fact, that stack that I'm talking about for the operating system that sits below your Buildpack layers, we build those with Dockerfile. That's because the stack is infrastructure, right? It's not an application image. So if you are an operator or a platform implementer, Dockerfile might be the right tool for you to produce base images for your organization. It just depends on what problems you need to solve. If you have some very custom processes that you want to create some kind of tool that captures those, maybe something like BuildKit is for you. If you are a very advanced wizard and you need a low-level API, and you write Go code, this is potentially for you. If you're loyal to the Java ecosystem and your organization is not polyglot and you only have Java applications, then maybe you can use Jib. Maybe the concerns about it not working with Python or Node just don't apply to you. But if you're an application developer who does not want to be concerned about what version of the operating system is running below your app and if it's vulnerable to Heartbleed or something like that, then Buildpacks are probably the tool for you. If you want to work on Spring Boot and add value to your business by adding features and focus on writing Java code, Buildpacks can separate you from those lower-level infrastructure concerns. Thank you for joining me today. If you would like to talk more about Buildpacks or about Heroku, we do have a booth down in the exhibit area. We'll be down there for the rest of the day, and please come and chat with us and ask us questions. Thank you.